Now for something completely different, something totally new today. Momentum and impulse. The good news is, especially the first day, it's not very hard. There are 3 primary conservation laws in science. Forget that, in the universe. Forget science. We've learned conservation of energy, which is intimately connected to the one you learned in chemistry, which is conservation of mass. The third one is conservation of momentum. So my little joke here actually applies to something called conservation of angular momentum, which we don't actually study. That's a first-year physics in university topic, depending on what physics course you take. Sometimes it's not till second year, but it's an angular momentum. But I mean, I think you can get an idea of what angular momentum means, because in this question, it's kind of cute, right? What are you doing? I'm spinning this way. Each turn robs the planet of angular momentum, slowing it spin the tiniest bit, lengthening the night, pushing back the dawn, and giving me more time with you. So that's pretty cute. I won't do that now, so your videos don't take any longer, but I thought it was cute. Anyway, so momentum is the topic of the day and for the rest of this unit, actually. And so what is momentum? Well, the main thing is, let's play Would You Rather. Would you rather have a cave troll run into you at full speed or Mary at full speed? And assume they have the same full speed. Well, I think you'd probably guess Mary, because he's itty bitty and a cave troll is huge. However, what if it was Mary at full speed and a cave troll at 0.001 meters per second, like in a barely sauntering? Probably it'd be worse to be run into by Mary if he was going full speed and the cave troll was going itty bitty, besides the fact that he might eat you. But other than that, just the collision itself wouldn't be that awful, right? Wouldn't be that awful. So, and the reason is that mass and velocity play together into giving you something called momentum, right? And that's all it is. So there's 2 properties that affect an object's momentum, right? And that is mass and velocity. So more mass is more momentum and more velocity. And I say a straight line means directly proportional. Okay? So momentum increases when either mass or velocity increase. And this is the idea of, so, Mary and the cave troll at the same velocity. Okay, the cave troll's got more momentum. You don't want to be hit by him. But if the cave troll goes slow enough, Mary could have more, right? Mary could have more momentum and it'd be more of a hit to be attacked by him or hit by him. So that means, because they're both directly proportional, momentum is just simply the property of mass and velocity, and that's it. Easy peasy. Momentum's an easy calculation. So let's look at the deets. The symbol is, I don't know why. I totally didn't make this up. But the symbol is P. P for momentum, obviously. And it is a vector. Okay, it's a vector because when you multiply a scalar by a vector, like mass times velocity, it remains a vector. Okay, and wait till calculus and vectors course to learn the details of that. Okay, and the units actually are simply, they're what they look like. It's kilograms times meters per second, which is just those, there's no special unit for it, like Newton or joule or anything like that. It's just these things, the product of mass and velocity units. Okay, you have to have these units, kilograms and meters per second, and yeah, it's a vector. Okay, and so that's going to come into play because two-dimensional momentum is quite a thing. Anyway, so let's just do a little example here of calculating momentum. Actually, we're not calculating momentum, we're calculating velocity, but we're using the momentum formula. And look at it, I didn't even put the vectors on top. A personal watercraft and its rider have a combined mass of 4 and 5 kilograms and a momentum of this. Determine the velocity. So we're given that the velocity, or the momentum is west, so the velocity will be west. Okay, that just stays the same. So whatever the direction on momentum will be the same as the direction on velocity. Okay, and so there's nothing to this, it's just a divide. So if you're lucky enough, and there will be probably on your multiple choice, a nice easy question, right, where all you do is apply this formula to find momentum or velocity, something like that. Okay, then there's something called impulse. An impulse is equal to change in. And you might remember that change in from, I think grade 9 math you do this, change in x over, or sorry, change in y over change in x for slope. Well, that's what this is, change in. Okay, so the formula for change in momentum is obviously second momentum minus first, maybe not obviously, but that's what it is. So then you can start looking at a little formula here, okay? And we're coming up with something. Again, let me tell you, the long story short is you don't need to develop this for me, but this is where it's coming from. So that would be, the second m, the mass doesn't change, but it has the second velocity minus the first. Factor out the m. And now look at this. Since I know that force is mass times acceleration, and acceleration equals this, then I could say, okay, well, then I'm going to replace in my force formula, I'm going to replace the acceleration, the mv2 minus v1 part, this part, with change in p. So then momentum is change in p over change in t, or sorry, force is change in p over change in t. So that impulse is force times change in time. So this is the formula, by the way. Circle that one right there, okay? Because that's the one you're going to use. So there's a little bit of development there. Like I said, I'm not going to ask you to develop any formulas on your test, but that's where it came from. It's just taking formulas that you already know and reapplying them and resubstituting. And if you want to ask me some more questions, if I went quick through that, you can tomorrow. But this is the long story short. This is the short story long. This is the long story short down here. So let's apply them. And this is the formula for impulse. Oh yeah. So this is even the more useful one. Since we know that impulse is mv2 minus v1, so then instead of writing, because like something you don't really ever measure is momentum. Like you don't really measure. You can calculate momentum very easily, but you don't measure momentum. You measure speeds and you measure masses, right? So really the impulse formula ends up being this, and this is the one that goes on your formula sheet. This is the useful one, okay? Ooh, scratched out. But anyways, that's it. Okay, so let's use it. So here we have a baseball, and it's traveling horizontally. We know its speed when it collides with the bat. The collision lasts, look at this, ms, you've seen this before, that's milliseconds. That means divide by 1,000, okay? Immediately after this collision, the baseball is traveling at 49.5 west. So it starts east, ends up west. And we want to find a few things, okay? First, we want to find the initial momentum of the baseball. So to do that, quite simply, here I wrote it. This is very important. You have to decide what's positive, right? So I said west was positive, just because that was the end. It doesn't matter. You can make east positive if you want. So there's all my knowns. Notice the t is divided by 1,000. Other than that, I want to find the initial momentum. So it's just mv. So mass times, now notice the v has to be negative because it starts east, which is a negative velocity. So my momentum is negative, or I could just call it east, whichever one. Okay. And in the second one, it says, what is the average force applied by the bat to the baseball? So I'm looking for a force now. And that looks scary, except for that we have this nice formula. This nice formula that we learned in the last one. This formula to find force. So as long as you know t and you know initial and final velocities and mass, force is an easy thing to find. Okay? So if you just follow through, you can see I'm just substituting in numbers. Force, I'm calling it force applied, is, and I'm assuming by the way, by virtue of this, I'm assuming it's the net force at the time. It's mass times v2 minus v1. So just rearrange it to get force by itself. So there's the mass. There's my v2 minus v1. Remember that this is negative, so it ends up being, 49.5 plus 37.5, which makes sense because change in velocity goes all the way from 37 east to 49 west. So it should be a really big number, right? And then in the very short time of contact. And it should be a big number. You expect that with these because, the baseball hits the bat, you feel it in your hand for one thing, but beyond that, you're really changing the speed of that ball, right? So that's it. That's using the momentum formula. So I guess the triggers to do that, especially it's a small thing, is in this unit. If you're just looking at this unit, if I'm asking you for force, this is the only formula that we use force for. That's an easy one. But it's a nice handy equation you can use, okay? All right, another example. Here we have a hockey puck. First, it's going at a nice, smooth, flat section of ice, 18 meters per second. Then it encounters some friction, right? Some snow that slows it down. So after 2.5 seconds through the new system, so it starts at 18. After 2.5 seconds, it ends up being 11 meters per second. And it asks us for the change in momentum, right? That's the delta P. Well, that's just simply mv2 minus v1. And there's no change in direction in this case. It's just going in the same direction. It's just that it gets slowed down, right? So our change in momentum, depending on what you call positive, right? I don't think I wrote that down, but we're just going to say the direction of motion is positive. We don't even know, right? But it is a negative momentum, and that makes sense because, or negative change, sorry, because it's slowing down. So it makes sense that even though it's not totally clear what's positive and what's negative, you know, because we're not given anything, you just say, well, the direction of motion is positive, so the momentum is negative in the direction of motion, which again, because it's slowing down, makes sense. Then it says, what impulse does the snow exert on the puck? Weird question, but impulse is just change in P. So, I don't know. I chose this example specifically because depending on what, you know, if you're looking at a textbook type question or something, they'll use different language for the same thing. Okay, I try not to be so tricksy, but. And then it asks for the average force of friction. Well, you're going, well, friction, there's no mu k or anything like that. We have just, the only force causing this to slow down is friction. So that's just going to be the force that you solve for in the equation. Okay, so force times time is the change in momentum. Solve for force, and that's all you do. Okay? Small number, but it makes sense. It's just a little hockey puck. Okay? I think that's it for impulse. Yep. Okay, that's it for today.